Morning. It's a little dark. Multivariate function we did last time. I finished with the limits. Looking at derivatives. Alright, so now we have more than one independent variable to take the derivative of. Right? Well, the idea is still kind of the same. Still trying to find a rate of change. Except now it's not with respect to specifically a variable, generally speaking. It's in a specific direction. This is the idea of partial derivatives. F of xy is a function of both x and y. The partial derivative function for two variables, there are two of them. You have partial f, partial x. So the partial of f with respect to x also is f sub x. Limit as delta x goes to 0, f of x plus delta x comma y minus f of x comma y all over delta x. Notice that. This y is being, this y here is being held constant, right? All we're letting change is our x value. If you ignore the y, isn't that just the derivative with respect to x? Isn't that the definition of the derivative with respect to x? Well, this means, of course, if you take the partial with respect to y, it's the same idea, except now we're letting the x be constant. Right, we're holding the x constant, we're only changing our y value. Again, the two types of notation, you have the partial f with respect to y or f sub y. They are used interchangeably. Consider the three-variable function f of x, y, z. Partial derivative functions, now there are three of them, right? definition, notice the similarities. There's partial with respect to x. There's your partial with respect to y. Third one shouldn't be a shock. The partial with respect to z. Notice here, you only let the z change. You hold everything else constant. And these definitions can be extended to more than 3 variate, right? So you have a 4-variate function. You'll have 4 partial derivatives, and their definitions are going to be very similar. So for this first problem, we're going to use the limit definitions to find the partials. And then we'll see if we can use some shortcuts. And notice, even though we're taking the limit of a 2-variate function, it's a single variate limit, isn't it? Only delta x is going to 0. I guess I should say that should be z, right, not f. That doesn't matter. Z of x plus delta x comma y. Everywhere there's an x, replace it with x plus delta x, and leave y alone. Subtract out f of x, y. Now expand it out. Two x squared plus 4x delta x plus 2 times delta x squared minus 3xy minus 3 delta xy plus 4y squared. Distribute that negative through the second term. Plus 2x squared or minus 2x squared. That's nice. A minus 3xy and a plus 3xy. A plus 4y squared, a minus 4y squared. Look at all the terms that we're left with now in the numerator. They all have a delta x in common, right? Factor it out. Left with 4x plus 2 delta x minus 3y. There's the limit we're left with once all the simplification is done. And what is that limit? What is it? There's your partial with respect to x. Comment on notation. Is there a difference between those two? What is it? So this one's saying find your change in x first and then square it. This is the change of x squared. So you square all of your values first and then find the change in those values. So they are not the same. By the way, that is also something completely different. That is a different kind of operator. So we can't use that either. Right, none of those three are the same. Here you have to be careful. These two could mean the same thing. Or this one could be read the change of the entire thing x times y. So avoid that ambiguity. Either put parentheses around your delta x, or write your y out in front. I'll leave that up there. Now we want to find the partial of z with respect to y. Using the definition, the process is
Heroic College at Burlington County.
It's important to leave a voicemail. Process is almost the same. In fact, it is the same, except we're letting y change now instead of x. So limit as delta y goes to 0. Z of x comma y plus delta y minus z of xy all over delta y. Right? Everywhere you see a y, it becomes y plus delta y. X's are left alone. And of course, we have our minus z all over delta y. Expand everything out. 2x squared minus 3xy minus 3x delta y plus 4y squared plus 8y delta y plus 4 times quantity delta y squared. Shoot the negative through. plus 2x squared minus 2x squared minus 3xy plus 3xy plus 4y squared minus 4y squared. All the terms we're left with in the numerator have a delta y in common. So factor it out. Left with negative 3x plus 8y plus 4 delta y. And then after all of your simplifications, that is the limit that we're left with. And what is that limit? There is your partial with respect to y.
I have a question. Why is that 8 and not 4? Like, I thought 4 for some reason.
Where?
For the 8y delta 5. I thought 4 for some reason.
So when you expand this term out, y squared plus twice their product, 2y delta y plus delta y squared, then distribute the 4 through. So because that middle term gets doubled, that's why it's an 8. Just like Calc 1. Just go to that one. Those definitions get hairy real quick. All right, that two-variable function we just looked at was real simple. It was just a standard quadratic in 2 variables. What happens when you start to get uglier and uglier functions? Now this definition doesn't become real practical. But we can still use the definition to come up with a method. Well, if you look at each one, right, the only variable that changes is the one you're taking the partial with respect to. Everything else is being held as a constant. And then using this question we just did, the process is identical to what was done in Calc 1. That would seem to imply just treat it as a Calc 1 derivative. Just whatever variables you aren't differentiating with respect to, treat as a constant. And what's the derivative of a constant? So partial of y with respect to x would be 0. Partial of z with respect to x would be 0. To start with x. Let's do this. So what I'm going to do is I'm going to rewrite in Z just to make it a little more obvious what's going on. Differentiating with respect to x, only the x is changing. All other variables are treated as a constant. That means 1 over y is a constant, right? Then from Calc 1, wouldn't that just be a scalar multiple rule? Scalar times the derivative of the function. What's the derivative of x squared? Multiplied by 1 over y. Sum rule, right? Derivative of sum of the derivatives. Plus, again, y is being treated as a constant, which means y squared is a constant. So it's going to be y squared times the derivative of 1 over x. What's the derivative of 1 over x? There's your partial with respect to x. Again, if I just rewrite z to make it more explicit. Partial of z with respect to y. Now we treat the x as a constant. That means x squared is constant. Derivative of 1 over y. That gets multiplied by x squared. 1 over x is constant. Derivative of y squared. That gets multiplied by your 1 over x. There's your partial with respect to y. That is all there is to partials. Probably the most common mistake I see with partials is not treating every other variable as a constant the right way. And so it takes some practice to start seeing every other variable as a constant. From Calc 1, d dx of sine of u is what? Close. Both of you are close. In fact, you said the same thing, just reverse the order once you put the u. You have the right idea. It have to be d dx, not cosine of x, sorry, cosine of u. Not just du, du is a differential. Okay, but you have the right idea, right? So don't forget your chain rule. Well, isn't z sine of u? What's u? What's the partial of u with respect to x? What is it? It's just 2. See? You just made that mistake that I just said. Remember, y is a constant. What's the derivative of a constant? So 3y is a constant. Its derivative with respect to x is 0. The 2 cosine of 2x plus 3y. Then the partial with respect to y. Now take the derivative of u, but this time with respect to y. What do you get? Just 3. And there's your partial with respect to y. d dx inverse tangent of u. From Calc 1, what is it? What is it? That would be if it's inverse tangent of x. This is inverse tangent of u. Times what? Which I'll just write in the numerator. Z. Is that a sum of functions involving x? It is, right? So we're just going to have to do each one individually. First term, taking the inverse tangent of x squared y. So what is that derivative with respect to x? Partial x of x squared y.
2xy over 1 plus.
And just 2xy. Then over the 1 plus u squared. X squared y squared is what? There's your first term. In the second, what are we taking the inverse tangent of? What are you taking the inverse tangent of in that second function?
Y squared.
What is it? Xy squared is what you're taking the inverse tangent of. What is the partial of that with respect to x? That's just the y squared. Now over 1 plus, what do you take the inverse tangent of? Square it. And there's your partial with respect to x. Right. If you're feeling adventurous, you could write that with a single denominator. Right, so you could write as a single fraction. If you're feeling adventurous. I'm not. So we're just going to leave it there. We're doing the exact same thing as we just did, except this time it's with respect to y. First function, what do you take the inverse tangent of?
Yeah.
What is its partial with respect to y? Oh, well, the good news is the denominator is going to be any different. Your second inverse tangent, what are you taking the inverse tangent of? Its partial with respect to y. 2xy. And again, the denominator winds up being the same. And you just made the most common mistake as well. It's not just 2y, because x is a scalar multiple. Right, so it's x times the partial of y squared, which is 2y. Right, so it's 2y times x. When you do enough of these, they'll become like second nature to you. If you want even, you're doing with respect to y, replace x with an actual number. Say x is 3. Now take the partials. Makes it easier to see what to do, right? So if you need to do that, just don't forget to replace them in your final answer. d dx of e to the u is what? What is it? This is the, right? What is u? What is its partial with respect to x? That's just now times e to u. Partial of u with respect to y now.
X plus x.
It's just, what is it? It's just x. X squared is a constant. Derivative of constant is 0. And then e to the u. f of xy, function of both x and y. Take the partial with respect to x. Look back. Is it still a function of x and y? So won't you be able to take its partial? So for instance, want to be able to do this? Right? Second order partial. But wait. Couldn't I also take its partial with respect to y? Now here's where you have to be careful. The order in the denominator. The proper order is read right to left. So that second order partial would be the partial first with respect to x, and then with respect to y. I'm not there yet. Pretty sure I know what you're going to say. I'm not at that theorem yet. But when you write it in this notation, the order is still read left to right. So that'd be first with respect to x, then with respect to y. Pretty sure you were going to bring up claret, right?
Well, I was going to say, I thought it didn't matter which one.
Yeah, that's claret. I haven't mentioned that yet. But then you can have a similar argument for partial with respect to y, right? So these are your second order partials. This is for two variant. These we call mixed partials, right? Because two different variables. Well, for two variant, how many second order partials were there total? Well, they're all listed, right? How many are there? There's four. Right? There's four second order partials. Are they all distinct? They're not. Claret's theorem states the order in which you take a mixed partial doesn't matter. That means your two bottom ones are identical. But we can keep going. Those four partials, aren't they still functions of x and y? Which means you could take each of those. You can take the partial of x and y of each of those. Those would be your third order partials. How many would you have?
8.
There's 8 of them. How many are distinct?
Well, if you like make the chart, then all the diagonals would be the same. So 4.
More than that.
6.
I think it's 6. No. Yeah. Right? XXY. You have the 3. XXX, YYY, ZZZ. Those are all distinct. That's 3. XXY would be distinct. That's 4. XXZ would be distinct. That's 5. YYZ would be distinct. Actually, is there 8? I think there's more than 8. Oh, never mind. I'm being an idiot. I'm thinking of 3 variant. There is no Z. What am I thinking? Okay, let's do that again. Right, XXX, YYY, that's 2. You have XXY is 3. YYX would be 4. I think that's it. Right, because XYX would be the same as XXY. Right, so any ones that have 2 X's and 1 Y are all the same. Any that have 2 Y's and 1 X are all the same. Yeah, it's 4. I was thinking of 3 variant for some reason. There's more than 8 3 variant. A lot more than 8 3 variant, actually. Actually, that's a good question. How many third order partial 3 variants are there?
16.
More. There's 27 of them. 3 cubed. How many are distinct? Right, because you're not going to have 27 distincts. That's where you have to try to start listing. Right, so I guess it'd be really nasty of me to go, okay, here's a 4-variant function. Find all the 5th order partials. Because that's 4 to the 5th. Which is 2 to the 10th.
24.
Yeah, it's 1024. I don't know how many of those are distinct. I'm not going to try and find out. But you get the idea. Right, so an n-variant function would have n to the m order partials. Not all of them would be distinct. Right, but also, generally speaking, it's more than half are distinct. And then obviously you can keep going. Right, so we could have a 10th order partial, and it could be mixed. But use Claridge's theorem to your advantage. If you're asked to find a higher order partial, remember the order doesn't matter. Of course, we're going to jump in the second order partials, the 3-variate. And here we won't use Claret's theorem, so we will actually find all 9 of them. Because here I think it's 6 distinct. Start with f sub x. Partial with respect to x. Cosine of what? It's just cosine of yz. Let's stick with that. Go away. Go with respect to x again.
It's cosine y and z.
What is it?
It's cosine y and z again, just because there's no.
What is it? It's 0. Remember, it's with respect to x, y, and z are constants, which means y times z is a constant, and cosine of that's constant. So go back to fx, take its partial with respect to y.
Negative sine y.
What is it?
Negative sine y.
You're missing a term.
Negative z sine yz.
Got chain wrong. Right, so I'm not looking at this function up here, we're just looking at fx. Well, we already dealt with that, right? When we took the partial. So now you ignore the original function. I'm just looking at f sub x. I'm taking those partials now. There's one more. So again, go back to the partial with respect to x. Take its partial with respect to z. What do you get? That takes care of all the second order partials starting with x. Partial with respect to y, now the original function. You can give an answer.
It's negative x z sine yz.
Negative xz sine of yz. Now stick with f sub y. Be methodical about it. Partial with respect to x.
Negative z sine yz.
Negative z sine
Yz.
back to the partial with respect to y. Take its partial again with respect to y.
Is it negative xz squared cosine yz?
Back to the partial with respect to y. Take its partial with respect to z. What is it? You said negative xy cosine of yz?
Is it negative x cosine of y?
This probably serves two purposes.
Negative x sine x.
Isn't it will be the same function but with the cosine?
You're overlooking it. I'm going to wait for the face plants into the desk. Because once I point it out, you're going to go, oh, that's really obvious. Remember, it's this with respect to z. Isn't this a function of z? Isn't this a function of z? Don't you have a product of functions? What rule is that? This is a product rule. You didn't think we lost product and quotient rules, did you? Oh, no, you used to have to keep those in mind, too. So start with, the order doesn't really matter, but I'll do negative xz times the derivative of sine of yz with respect to z. So what's the partial of sine yz with respect to z?
Negative x cy cosine yz.
Now keep the negative x sine of yz multiplied by the partial of z with respect to z, which is what? So it's partial of z with respect to z.
Negative x sine yz.
There's FYZ. That was the second purpose of this problem, to remind you of product and quotient rules. Right. There's a reason why this wasn't a product. Because that's just X, this is Y and Z. It's not like it's X and then there's an X in here. It's not a product of two functions of X. Right, same thing with these here. This isn't a product because you're differentiating with respect to X. That's X times a constant. Differentiating with respect to Y, that's a constant times your function. Now when it's with respect to Z, it's a constant times function, which is product rule. It would be the same argument with quotients. We have a fraction and it's function of X with Y's and Z's in there, and then over a function of X, Y's and Z's, now you have quotient rule. Because both numerator and denominator have X involved. That line doesn't look straight. You just have to now retrain yourself. So train yourself now to look at these as multivariate functions. Train yourself to look at, for instance, when we do the FYZ, train yourself to look at this as a constant, and then two functions of Z. Once you get there, partial derivatives are easy. They're essentially Calc 1 all over again. But you have to get there first. Are there any questions on what we've done today so far? We will continue this problem on Thursday. Pretty sure homework 12 is up, but that's not due until next Thursday. It is up early. And you also have the project due, I think that's the week before spring break. But what day is that? I think that's that's Friday. That's literally just before we go on spring break. Your third project will be due. And the third, oh, that's right. The third project is that Speedo question. The LZR Speedo Racer, something like that. It's a fun project. I'll see you on Thursday. We'll pick up here, and then we'll look at what's next. Oh, tangent planes and chain rules as well. Thank you too.